right, you all ready to get yelled at for 2 hours? Yes, you're ready? Okay, all right. So it was requested of me to start on the new material. And just to kind of put it all into perspective, the new material is about, I would say, like half a midterm. So expect like at least 10, maybe 10 questions on the final exam to be new material. And so that new material is the second half of electrochem. So like the Nernst equation, electrolysis, corrosion, batteries. And then chapter 21, nuclear chemistry. So yeah, anticipate about 10 questions from there. Your final exam is 50 questions. So really a good rule of thumb is just like 10, 10, 10, 10, 10. Basically 10 questions from every previous midterm, 10 questions for the new stuff. I think that's a good rule of thumb, all right? So let's go over new stuff. All right, so part 2 of electrochemistry really goes along with our discussion on thermodynamics and how when we use table values, whenever you see like delta G naught, what does that naught mean? It means standard conditions. Standard conditions, so like 1 molarity, 1 ATM, 298. Do you have to build batteries at standard conditions? You do not. You can use whatever concentrations you want. So we have to use a different type of equation to calculate cell potentials at non-standard conditions. So whenever we use the equation E cell naught, notice naught meaning standard conditions, when we calculate E cell for a voltaic cell, it's typically the reduction potential at your cathode minus your anode. Both of those numbers are reduction potentials. We take them straight from the reduction potential table just as is, as long as you correctly identify what your cathode, what your anode is. So when you do that, pretty straightforward subtraction, what you're calculating is the cell potential if you make that battery at standard conditions. But if your concentrations of your battery are not at standard conditions, you have to use the Nernst equation. So let's look at this reaction. We got zinc and nickel, and I already tell you the cell potential is 0.48. So this number was gotten from doing just cathode minus anode. I just did it for you, right? So is this reaction spontaneous, yes or no? Yes, because our cell potential is positive. So this reaction is spontaneous in the forward direction. It's a battery, it's a voltaic cell. So once we start this, this redox reaction, the cell at standard conditions, and it starts to go from reactants to products, how does things change in this reaction? How does the concentration of nickel change? Increase or decrease, or not change? It's going to decrease. Yeah, don't think about it too hard. Nickel 2+ is simply a reactant. So if this reaction happens, we're going to consume reactant. And then on the reverse side, zinc 2+ concentration will increase because it is a product. All right, nickel 2+ decreases because it's a reactant. All right, so at standard conditions, the concentrations of everything are what? 1 molarity. So Q at standard conditions is what? Let's calculate it. So let's look at this equation. It's zinc solid, nickel aqueous. So this is the same Q, K stuff as earlier. We're not going to include any of those solids. Our Q expression for this redox reaction is simply zinc 2+ concentration over nickel 2+ concentration. So at standard conditions, you told me anything with a concentration is 1 molarity. So at standard conditions, Q is equal to 1 molarity over 1 molarity. Once we're at standard conditions. So Q is equal to 1 at standard conditions. But you just told me as this reaction moves forward, concentrations change. So is our value of Q going to remain 1? Nope, it's going to change. So with our answers from parts 1 and 2, how does the value of Q change? It's going to what? Increase, yeah. Or think of it this way, okay? As your reaction moves forward, you make more product. You have less reactant. What is Q? What is K? It's products over reactants. So it makes sense that the value of Q is it's growing, it's getting bigger, because you're making more products. So what we see here is, yeah, Q increases as the reaction moves forward, all right? Q gets bigger because we're making more products. So then therefore, how does the measured cell potential change as Q grows? So we're gonna use the Nernst equation to inspect this. The Nernst equation, we do give it to you. E cell, this is like what you measure. Notice that there's no not here. It means at non-standard conditions, is equal to your cell potential at standard conditions minus 0.0592 volts over N log of Q. And so we do give you the Nernst equation on the exam. You just need to know when to use it. And we use it when we are at non-standard conditions, when I give you concentrations of stuff, all right? So when we're at standard conditions, Q is equal to 1. What is log of 1? 0. So when we're at standard conditions, look, what you measure is your cell potential at standard conditions. So that kind of proves that those table values are only good when we have 1 molarity concentrations, we're at standard conditions, all right? But in this example, we're thinking about how does Q change. So thinking about, rules with logarithms, as Q increases, you can like type it in on your calculator. Log of Q increases, like that whole thing, this whole term increases as Q becomes a bigger number. So basically, as Q increases, we are subtracting a larger and larger number from our standard cell potential. So how does our measured cell potential change as Q gets bigger? It goes down. Yes, it goes down. Does that make sense? New batteries, like if you have a AA battery and you use a voltmeter and you check the voltage, it's going to be the highest potential when it's fresh out of the box. Right? Versus if you take an old AA battery and you test the voltage, it's gonna have a lower potential because you've spent a lot of the reactants and converted it into products. But if we wanna sound smart and use the Nernst equation, really what an old battery is, once you've used a lot of it, is you've converted a lot of reactants to products, Q is bigger, this minus term is overall bigger, and so what our measured cell potential is going to be lower. So this is how you like check like a car battery if it's good or not. So like these lead acid batteries, typically you want like a higher voltage of your car just sitting there off, like around 14 volts. But if you measure a car battery and it's closer to like 12 or 13 volts, then maybe it's time to start think about saving up to replace your battery. Because older batteries have a larger Q, you generate more products, and it makes your measured cell potential lower than standard cell potential, all right? So that's the idea. That's why batteries eventually go dead, because Q grows and you subtract a bigger number from that standard cell potential. All right, so that's just kind of conceptually like why batteries go dead. So let's just do the calculation because the numbers prove it as well. So let's calculate what is the EMF, or essentially cell potential. We're just calculating cell potential when we have these concentrations. So we're actually going to plug in a number here. We're still going to use the Nernst equation, right? So given this question, I give you E cell. We need to figure out N, and we need to figure out Q. So Q is going to come from the equation. So products over reactants. So, Q is equal to the zinc concentration over the nickel concentration. So this is equal to, 1.75 over 0.25. So Q is equal to something. Is that right? Yes, it's equal to 7. All right, and so we're going to shove that into that expression. We just need to get N. And so to get N, we want to look at the balanced chemical redox reaction. All right. So this is the same N that we canceled in the background when balancing redox reactions using the half reaction method. But there's a lazy way you can get N. Do you want to be lazy with me? Yeah, okay. So to get N, just focus on like how one thing is changing and how many electrons it's either gaining or losing. So let's just focus on one thing, zinc. All right? We are going from zinc solid to zinc 2+. So, I mean, just kind of use your intuition. How many electrons are going to be involved in that? 2, all right? 2 electrons. So that is essentially what N is, all right? Notice that if you do the same treatment to nickel, you'll get the same answer, that, oh, 2 electrons are involved there as well. And that's because that's the electrons canceling in the background. 2 electrons come from your oxidation reaction, 2 electrons come from, go to your reduction reaction. So N is 2. So we don't actually have to like deconstruct the half reactions to get what N is. Usually you can just tell by charges or oxidation numbers. So putting this all together, the cell potential we actually measure is related to the cell potential at standard conditions, which I gave you, what was it? 0.48 minus 0.0592 over 2 log of 7. Before I calculate anything, this Q, what do I have more of right now? Reactants or products? Products. So what do you think the measured cell potential will be? Will it be higher than standard or lower than standard? Lower, because you basically packed a lot of products, and products isn't what generates the voltage. It's having reactants. Packing lots of reactants there will generate a lot of voltage, all right? And so yeah, the answer we get is a little bit lower than standard. It's 0.45 volts, all right? All right, so that's the Nernst equation. These are real life batteries, batteries with actual concentrations that aren't 1 molarity. All right, let's do one more. Okay, cell is constructed as written, calculate E cell. So notice there's no not there. That's not a mistake. It's trying to tell you, hey, this is not at standard conditions. So we probably want to use the Nernst equation. So E cell equals E cell naught minus 0.0592 over N log of Q. So whenever using the Nernst equation, the components you need the cell potential at standard conditions. So that means we have to do the cathode minus anode stuff. We need N and we need Q. So let's just do this in order. So in this question, I didn't give you E cell naught, so we have to do cathode minus anode, meaning we have to decide what is our cathode, what is our anode. So this is kind of like review from chapter, or I guess midterm 4. So ask yourself, how is silver changing? It's going from +1 to 0. So silver is being reduced. Yes, reduced. So it is our cathode. And lead is going from 0 to +2. So lead is being oxidized. It's our anode. So to get the cell potential at standard conditions, we're just going to do cathode minus anode. So let's locate those on this chart. So here is our, what's silver? Cathode. Lead is our anode. So what did I just say? This is my cathode. Here's my anode. So my cell potential is 0.8 minus negative 0.13. So my standard cell potential is 0.93 volts. Okay. That's if everything was 1 molarity, but it's not, because I gave you other concentrations. So we got E cell, let's get N. Can you lazy your way through this? Can you tell me what N is? It's 2, yeah. So you notice lead is losing 2 electrons because it's going to lead 2+. But you might be thinking, hey, but silver is only gaining 1 electron. What gives? There's 2 of them, yeah. So see how it all matches? Yeah, okay. So yeah, N is 2. And then what else do we need? Q, we need Q. So Q comes from the balanced chemical reaction. So make sure you have that or figure out what it is. Sometimes, you know, adding those two, this is where coefficients matter, right? Because when we choose what our cathode and anode is and calculate E cell naught, do we care about what the coefficients are? No, it's just about what's the cathode, what's the anode, cathode minus anode. But when we calculate Q and use the Nernst equation, we actually do care about the stoichiometry because Q, the stoichiometry ends up in the coefficients. So, or sorry, the exponents. So Q is equal to lead concentration over silver concentration, and it is squared. Yes, you'd only know that square is there if you had the balanced equation. So placing those numbers in, lead is 0.01, silver is 5 squared, and so this answer is 4 times 10 to the negative 4. So if this is Q, you have a lot of what right now? Reactant or product? Yeah, reactant. Yes. So is our measured cell potential going to be bigger or smaller than standard? Probably bigger because we have a lot of reactant. So just plug all that junk in and you'll get an answer. So what we measure is equal to standard 0.93 minus 0.0592 over, what did we say N was? 2, log of a small number, 4 times 10 to the negative 4. And yes, we get a slightly bigger number, nope, that's not it, 1.03 volts. So a little bit higher than normal, and that's because we packed a bunch of reactant in it. All right. Okay. All right, so let's talk about corrosion. And really it's just applying the ideas of what we discussed for midterm 4, that reduction potentials, the magnitude, tell us what substances are easily reduced or substances that are easily oxidized. So we can think about definitions here, how they're related. Actually, yeah, okay. So in this question, I'm asking what substances can offer cathodic protection to prevent the corrosion of elemental iron rusting, all right? So corrosion is explained by these equations. So the big takeaway is that what corrosion is turning iron solid into iron 2+ aqueous. And so this is kind of a precursor to rust. This is why you don't find a lot of iron artifacts out there, like really old iron things, because iron oxidizes spontaneously in the presence of oxygen and acid. Oxygen is everywhere. Acid is everywhere because like our rainwater is slightly acidic, excuse me, because CO2 is everywhere. So basically, if you look at, you know, the anode and the cathode and you do cathode minus anode, you see that this reaction is spontaneous. It has a positive cell potential. So rust happens on its own. So because we live in an industrial age, we want to prevent rusting. Lots of things are made out of iron and we want to protect the things that we build. So here are a bunch of different reduction potentials and values of different materials that may or may not offer cathodic protection. So the idea here, all right, is we want to look for a substance that is easier to oxidize than iron, solid, all right? So what we are looking for is what's called a sacrificial anode. Sacrificial anode. We want to replace the anode with a substance that is easier to oxidize. Because if we basically allow another substance to oxidize instead of iron, then we protect that iron, all right? So notice the reduction potential of iron is negative 0.44 volts. So if we want to look for a better anode, something that is easier to oxidize, what kind of reduction potential are we gonna look for? reduction potential that's more positive or more negative than iron? More negative, because we know that very negative reduction potentials make really good anodes. So I hope you recognize, oh, we're going to focus on these guys. They are better anodes than iron. But what component is the anode? Is it zinc 2+ that provides the cathodic protection? No, it's actually the zinc solid. Because remember, in the forward direction, what kind of reaction is this? Reduction or oxidation? Reduction. So if we're talking about the anode, we're talking about oxidation. So it's actually the zinc and the aluminum that provide the cathodic protection to iron. So our answer is aluminum and zinc. Those two things offer cathodic protection. And actually, if you go to Walmart and look for sacrificial anodes, which you can, they will be aluminum. So for example, your water heater, if you have an electric water heater, there is a sacrificial anode inside of there to protect the iron lining on the inside. So if ever you're a homeowner and you're like, your electric water heater goes out and you're like, oh my gosh, why? Before you like buy a whole new water heater, it might just be your sacrificial anode needs to be replaced. And that's like $20 at Walmart. It's not like hundreds and hundreds of dollars of what like a water heater is like. And so what this sacrificial anode does is, again, sacrifice itself instead of corroding the iron lining inside of your water heater. I also, I have a RV that has a water tank in it and also has a sacrificial anode in it. And so like a brand new aluminum anode just looks like a hunk of aluminum. But when I pull the old one out, it's like all eaten away and literally like all of this like white material comes off of it. It's just like a little like, I don't know, like piece of metal. So once it's spent, it's literally, again, that piece of metal sacrificing itself to protect the iron that's inside there. All right. Okay, so that's cathodic protection. Cool. All right. So using this same table, let's answer these questions. So let me just delete that real quick. All right. Which substances are capable of reducing zinc 2+? All right. So let's think about zinc 2+ and reduction. So zinc 2+, when it's reduced, it gains 2 electrons and it makes zinc solid. So if we're reducing zinc, is zinc going to be the cathode or the anode? It's going to be the cathode. So let's just go ahead and write that reduction potential. It is equal to negative 0.72 volts. So we are looking for what? So we've decided, okay, zinc is the cathode. So we are looking for which anode will produce a positive cell potential, because that means a spontaneous reaction. So if zinc is our cathode, which one of these things, what, aluminum or lead, has to be our anode to make this reaction spontaneous? Aluminum or lead? Aluminum's going to be our anode, right? Okay, but what substance is doing the reducing? It's the solid. Very good, because again, the reverse direction is oxidation. All right, so let's do it the other way. What substance is capable of oxidizing iron? So in an oxidation reaction, iron is going to lose 2 electrons. All right, so that means iron is at the what? Cathode or anode? Anode. So we decided what the anode is now. Okay, so iron is the anode. This is the anode. Okay, the anode has a reduction potential of negative 0.44 volts. So if iron is the anode, which one of these things have to be the cathode to be spontaneous, lead or aluminum? Lead this time, but what form of lead? The ion one, yes, very good. So here, this is going to be our cathode. Cathode means reduction, so we're looking at the forward direction. So yes, it is going to be lead 2+. All right. So it's all about wording, all right? So you can think of it this way. Lead 2+ is the oxidizing agent because it's reduced. Iron solid is the reducing agent because it's oxidized, all right? Okay, great. All right, last one. All right, electrolysis. So electrolysis is all we're doing is forcing a non-spontaneous reaction forward. The identity of your anode stays the same. The identity of your cathode stays the same. It's just we're forcing the reaction forward. So we don't switch definitions, right? Cathode, reduction happens at the cathode. Oxidation happens at the anode. All of that stays the same. It's just we're forcing this reaction to happen because it's non-spontaneous. So how do we force the reaction forward? We plug it into a wall, right? We deliver it some type of current, some kind of speed of electrons. And so the new unit here is amperage or current. And this is very flashcardable. You just need to memorize that an amp is the same thing as a coulomb per second. So if I have a current of 10 amps, what this means is that you are delivering 10 coulombs per every 1 second. And that's what you need to know. And then at this point, it just becomes advanced dimensional analysis, right? So there's our amperage, coulombs per second. What you also need to know is that Faraday's constant, that 96485 number, has the unit coulomb per mole of electrons. So what that means is that for every 1 mole of electrons, you deliver 96485 coulombs of charge. That is Faraday's constant, right? But here's the thing, when we're doing electrolysis, we aren't focused so much on the electrons, but what we're measuring is how much solid like electroplates out. So what we also need is a balanced chemical half reaction. We're producing chromium in this reaction, so we need to know what's the relationship between chromium and the number of electrons. So notice I'm telling you, okay, we are electroplating chromium solid, but it's coming from chromium with 3 chlorides on it. So what is the charge of chromium right here? So it's chromium what? +3, all right? So you can just kind of do a lazy half reaction. To go from chromium +3 to chromium solid, how many electrons are involved? 3. Right? And then so this is just stoichiometry, but really it's N, right? That in order to make a chromium solid, you have to deliver 3 moles of electrons. So those are 3 different equalities, fractions that we'll use in this analysis. So what are we doing? For 6 hours, we are delivering this current. So we need to convert hours to seconds. So 1 hour is 60 minutes. 1 minute, 60 seconds. So I think this is 3,600 seconds, right? So once you're in seconds, you can use the amperage. So for every 1 second, you deliver 10 coulombs. But I don't want coulombs, I want moles of electrons. So this is where I use Faraday's constant. So this is, 96485 coulombs is 1 mole of electrons. So the 96,000 number goes where? On the top or the bottom? Bottom. So 96485 coulombs, 1 mole of electrons. Perfect. But do I care about mole of electrons? No, I want chromium. What's the ratio? Is it 1 to 1? No, it's 3 to 1. So for every 3 moles of electrons, I get 1 mole of chromium. And it's all about the charge. Right? I told you via the charge. So if I was talking about like copper nitrate, if we were depositing copper nitrate instead, or copper from copper nitrate, what would N be here? 2, because it's copper 2 plus, all right? Okay, great, so it's all about the charge. All right, moles of chromium, and then finally just the molar mass. So 1 mole of chromium is 52 grams, and then it equals something, I don't know, whatever. Something, 39 grams of chromium. Okay, it's a nice chrome plated whatever. Okay, so that is electrochemistry and the rest of it. So yeah, move on to nuclear. Yeah, okay, all right. Okay, nuclear chemistry. All right, you just need to memorize like 4 different types of particles for nuclear decay. All right, so you just need to memorize this. We got alpha particles, we got beta particles, we got positrons, we got electron captures. And then also gamma. So we need to know, what do these particles mean? So alpha particles are really just a helium nucleus. So it has a mass number of 4 and 2 protons. So I'll just remind you that this type of notation that I'm using, this top number is your mass number. So this is your number of protons and neutrons, everything that's in your nucleus. But then this bottom number is just your number of protons. So that is tied to the identity of the element that you're focused on. Like if it's uranium or something, then that's 92 protons, I think. I don't know. I always forget. Yes, 92. Okay. So that's an alpha particle. Beta particles, on the other hand, have no mass and are a -1 charge. They're essentially like an opposite of a proton. Okay, but they have no mass. Or you can think beta particle is like it's like an electron, but it originates from the nucleus. Because when we think about, like, remember Chem 1210? Orbitals and stuff, right? Like S, P, D, and all of that, yeah. Those were cute. Those electrons were always like on the outside, the cloud, okay? So when we're talking about like electrons for nuclear reactions, these electrons, like this beta particle, it's actually originating from the nucleus. So these electrons are absolutely different than like our S, P, and D electrons that we talked about previously. Because in nuclear reactions, we are actually creating new elements because we're changing the composition of our nuclei. No longer are we thinking about just the electrons in the electron cloud. All right, so that is our beta particle. Next, we have positron emission. So a positron is like an electron, but just with a positive charge. Again, originates from the nucleus. And then electron capture. So this is an electron. So it has no mass and a -1 charge. But the differences here for electron capture is that it's a reactant. All right. While all of these other things, beta, alpha, positron emission, notice it's the word emission, so all of these things are products. And then the final thing here, gamma, a gamma ray, it has no mass and no charge. It's just literally pure energy. And this will always be a product also. So gamma radiation doesn't actually change the identity of anything. It's just pure energy, right? So do notice where these arrows are. And so how we balance nuclear reactions is we're simply just looking and conserving the number of protons and neutrons in the nucleus. For once in your life, for the first time ever, you are allowed to ignore charge. So we don't actually care about the electrons in the electron cloud anymore. All we care about is the composition of the nucleus. So we are ignoring charge completely. All we care about is the protons and neutrons. So if a beta particle is emitted by copper 66, it's about reading comprehension here. Copper 66 is our reactant. The beta particle is our product because it's emission. So I'm going to put copper over here. 66 is the mass number. How do I get the number of protons? Yeah, the periodic table, all right? So it's 29, all right? So copper is our reactant. So it's asking what is the product? So simply, we just need to place that beta particle with the correct numbers and then just make sure that the numbers of the mass numbers and our number of protons match. So the missing piece is going to have 66 mass number, but in order for all of this to be balanced, how many protons does this missing piece have to have? 30, yeah. So what happened is a neutron yeeted its negative charge and became a proton, all right? And so if it has 30 protons, now it is what? Zinc. All right, so we changed its identity. all right? And that's how we approach all of these. So we can do copper 66 again, all right? What has to be here? So this time we're emitting an alpha particle. So again, emission, put it on the product side, 4, 2. The missing piece has to have what, 62 and what, 27. What is that? Cobalt. Easy. See, we are absolutely ignoring charge. We don't care about electrons anymore. All right, positron emission of iron 53. So 53 iron, Fe, and then iron is 26. So if it's positron emission, where am I going to put the positron on the reaction? Reactants or product side? Product. So we got something. Our positron is a +1 charge. So my missing piece has 25 protons. So whatever that is, manganese. And then finally, this last one is weird. Electron capture. So calcium 38 has 20 protons. So this time the electron is going to be a reactant. So -1 number of protons there. All right. And so notice it's just one product here. So 38, and I think this is 19. So it is potassium. Cool. All right. So reading comprehension. Right. So like there's tables and stuff and it says like, oh, if your particle undergoes alpha emission, how does your like mass number and number of protons change? I feel like you don't have to memorize it as long as you know what an alpha particle is and how to balance the equation, you can just figure it out on the fly. Right. So like me personally, I don't memorize things. I just like think my way there. All right. Okay. All right. So this one. Okay, so we can actually predict whether a substance undergoes alpha, beta, or positron emission based upon the composition of its nucleus. There are 3 rules. 3 rules, right? So the first rule is anything that is heavier than bismuth, which has how many protons? 83. Will always undergo alpha emission, right? Look at the periodic table. Look at the one up there, right? Notice bismuth has a molar mass. What is it? It's like 209 point something, right? Okay. Then look at one element over, polonium. Look at its molar mass. How is that molar mass shown? It's in brackets. It's in brackets because polonium does not exist long enough for us to get a really good molar mass. Look at everything heavier than bismuth. Notice how everything has a bracket, and that's because anything heavier than bismuth undergoes alpha emission because none of those nuclei are stable. Bismuth is the heaviest stable nuclei on our periodic table. Everything else is basically man-made, right? It'll always decompose into something else to get more stable. So yeah, anything heavier than bismuth will undergo alpha emission to basically make itself lighter, so then it can become more stable. So that's the first rule. The second and third rule go together, and this is based upon your neutron to proton ratio of your nuclei, right? So there's basically 2 scenarios. If your neutron to proton ratio is too high, right, then what happens? You all should just learn this. Okay, it's beta emission. I think. Is it? Does that sound right? I don't know. I don't memorize things. My hand just knows what the answer is. Okay, and then on the other hand, if neutron to proton ratio is too low, it's the other one. It's, what is it? Positron emission. All right? I'll prove it to you, all right? Okay, so let's go through these. So, and technically, you do not need this belt of stability to answer any of these questions, all right? So it's a portion of your textbook that shows the 3 different scenarios that you can have, that all of these scenarios help us get to an element that is more stable, all right? So technically, all of these, you don't need the belt of stability to answer the question. it's pretty obvious whether your neutron to proton ratio is too high or too low. So let's look at the first one, potassium 40. We just need to decide how many neutrons, how many protons are there. So someone asked, could something too low also be electron capture? That is also correct. Yes, electron capture it has the same net effect as positron emission, right? Okay, so potassium 40 has how many protons? 19. And then how many neutrons? 21. So its neutron to proton ratio is 21 over 19. So it is equal to something, I don't know. It is equal to 1.11. All right. So for fairly lightweight elements, the preferred neutron to proton ratio, is 1. That nuclei tend to prefer having an equal number of protons and neutrons for fairly light elements, but as you get heavier and heavier and heavier, more neutrons tend to be more dominant, all right? So this neutron to proton ratio of 1.11 is too high. So that means potassium 40 is most likely to undergo beta emission. But I want to prove to you that doing beta emission gets that neutron to proton ratio down lower. So when potassium 40 does this, what is it? So potassium 40, 19 protons. What is made when a beta particle is emitted? We have something with 40 protons. How many neutrons? 20. This is calcium. What's the proton-neutron ratio for this calcium 40? It's 1, right? 20 protons, 20 neutrons, it's a perfect 1. So this shows you that emitting a beta particle lowers that neutron to proton ratio because a beta particle converts a neutron to a proton, all right? So that neutron to proton is 1. Another way you can tell that potassium 40 is too heavy, has too many protons. You look at your periodic table. Tell me what is the molar mass of potassium? 39 points. Crap. So that means, what do you think the most abundant isotope of potassium is? Potassium 40? No, it's probably potassium 39. So that means potassium 39 is stable, all right, because its molar mass is like around 39. So having potassium 40 is, again, has a little too much, too many neutrons there, right? Okay, so there's that one. All right, plutonium 244, what does that undergo? Do I even need to do a neutron to proton ratio? No, because plutonium has 94 protons, so this is gonna undergo alpha emission to become lighter. I mean, it's gonna take a couple steps for it to eventually become stable, but because there's too many protons there, right? Okay, great. Until it gets like lighter than bismuth, right? Oxygen 14, neutrons, protons. So oxygen has 8 protons. How many neutrons? 6. So this proton to neutron ratio is 0.75. So that ratio is obviously too low. So it has to undergo some type of emission to become more stable to get it back closer to the belt of stability. So what is this? It's gonna be positron emission. So again, I wanna prove it to you that positron emission will make it more stable. So we have oxygen 14, it has 8 protons. It emits a positron, so 0 plus 2e. So what's that missing piece? 14, 7, nitrogen. What's the neutron to proton ratio here? 1. Is nitrogen 14 stable? Yes, because it has a neutron to proton of 1. But how else could you know that nitrogen 14 is stable? Look at the periodic table. What is the most abundant isotope of nitrogen, just based upon its molar mass? 14, all right? Yes. All right. So that's how we kind of interpret it on the fly. Cool. All right. All right. So the example I gave with plutonium, that because it's a heavy element, heavier than bismuth, it undergoes alpha emission, but just one alpha emission won't make it stable. So this is where the nuclear decay series comes into play, where a lot of these lanthanides and actinide series, just the actinide series elements tend to undergo multiple decays in order to get stable. And it can take upwards of 13 steps for, like, for example, uranium to be stable. So what we can do is ask you, okay, after these 5 steps, these 5 nuclear decay steps, what is your resulting product? So the idea here is we just do decay after decay after decay, kind of consecutively to see what the final product is, all right? So in this question, thorium-232 decays by alpha, 2 betas, then 2 alphas. What is your product? So there's a lot of ways you can do this. So you can do one at a time if you wanted to. All right, so thorium 232, and then you need the number of protons, so that's very important, so 90. So it's gonna be helpful for you to maybe memorize some of these elements, the common ones like thorium, uranium, curium, bismuth, those ones that are common for nuclear reactions, because I don't want you to get stuck in a jam and be like, ah, crap, what is thorium, right? So thorium is 90 protons. So what's happening? We're doing an alpha, 2 betas, then 2 alphas. So you can either, because remember, when we do these nuclear reactions, the nuclei, masses and stuff, they're conserved. So we can bulk all the steps together, or we can do them one at a time. So in my mind, I'm lazy. So I'm just gonna bulk them together, all right? So if we do 3 alpha emissions, 1 alpha particle, is mass number 4, 2 protons. So 3 of them is equivalent to what? 12 mass number, 6 protons, right? Yeah. So what does the missing product have to be if we lose all of these alpha particles? What is that mass number? 2, 20, and what else? 84. So notice that these numbers and these numbers add up to these numbers. Do they? They do, okay, all right. But those are just 3 alpha emissions. I need to then do 2 beta emissions also, right? So 2 beta emissions is equivalent to, again, 0 mass number, but -2 protons, all right? So notice I don't even care what this intermediate step is, I just care about the last thing. So what is the identity? What's the mass number of this product after 2 beta emissions? Still 220, but then how many protons? 86, yes, because remember, this is your product. So these 2 things have to add up together to the previous thing. So what is 86? Radon. Okay, RN, radon, very good. Perfect. So yeah, I think that's the answer. Is that the answer? Yes, so in my key, I did every step individually, but you don't have to do that. You can just bulk them all together if you want, because it doesn't matter, because the nuclei conserve itself. All right, so the last part of, I guess there's 2 extra parts for nuclear chemistry. One of them is kinetics, but this is no different than the kinetics we did in chapter 14. So if you're good with that, the integrated rate law equation and half-lives, then these nuclear equations will be the exact same, all right? So it's all about reading comprehension. But what's the one thing you need to know about nuclear reactions? They all follow what kind of kinetics? First order. So the equations we care about are the natural log ones, all right? And then our half-life equation, which is natural log of 2 over rate constant. So I tell you a certain radioactive sample reduces by 35% after 2 days. Calculate the rate constant, calculate the half-life, and then calculate what percentage it remains after 1 week. So this is just chapter 14 stuff. Do you need me to go over it or not? Okay, all right. So natural log of A sub t equals natural log of A initial minus KT. That is your first order integrated rate law, right? It's reading comprehension. We need to figure out what is A sub t, what is A sub 0, all of that. And that will help us get the rate constant because I give you time. So let's do a reading comprehension here. If my sample reduces by 35%, what is A sub 0? What do I start with? 100%. What is A sub t? Is it 35? No, it's 65. So those are the numbers I put in. So using the integrated rate law, we're going to simply do A natural log of 65 equals natural log of 100 minus K, that's what we're solving for. T is 2 days. So when we solve for K, it's going to have the unit of inverse days. So when you do that, you get K is equal to 0.215 days to the negative 1. That is K. Is that fast or slow? I don't know. So that's the reason, like K, it's hard to tell what the speed is. So that's why we take K and convert it into a half-life, because half-lives have more meaning to us. So B is calculate the half-life. All we're doing is just putting address on the rate constant to make it more palatable to us. So the half-life equation is half-life is equal to natural log of 2 over the K we just got, so 0.693 over 0.215 days to the negative 1. So if you calculate this, you get T1 half is 3.22 days, right? So about 3 and some change days is the amount of time it takes for you to lose half of your sample, right? For a second, let's just make sure this answer matches all the other information we were given. So if I gave you your sample reduces by 30% in 2 days, does it make sense for your sample to reduce by 50% in 3 days? Yes, that is good, right? Because if it was like the other way, then that would be all messed up, right? So we want to make sure that our answers, match. All right, so that's our half-life, 3 and some change days. All right, what percentage of your sample remains after 1 week or 7 days? So there's a couple ways you can do this. You can either use the integrated rate law. That's probably what I would do, because 1 week, 7 days, that's T. We already know what K is. So I would just stick those numbers into the integrated rate law. So natural log of A sub T, that is what I'm solving for, equals natural log of 100 minus K 0.215 days to the negative 1, 7 days. All right, so we're just doing A again, but this time a different amount of days, figure out how much is left after that amount of time. And so we get, I think, 22.2% is left over, right? So it's a little bit more than 2 half-lives. Right. Another way you can do it is calculate how many half-lives are in 7 days. But honestly, if you are just good with the integrated rate laws, then you don't even need to think about the half-life. Okay, good? All right, so someone asked, do we need to know about particle accelerators and cyclotrons? So those are 2 facilities or instruments we use to do transmutation reactions. So transmutation reactions are just other ways we can balance nuclear reactions. So notice in these questions, these are all decay reactions, all right, where one thing becomes 2 things. But in transmutation reactions, we're actually smashing atoms together. So we might have 2 things combined to give either one or multiple things. But how we balance them is literally exactly the same. We want to make sure that our mass numbers and protons are conserved. So cyclotrons and particle accelerators, that's just where we do transmutation reactions. And the one thing I wanted to mention is the last section where we talk about energy of nuclear reactions. You notice that many of the examples that I show here are like heavy actinide series elements. So those elements oftentimes undergo decay reactions because they're unstable, but also those types of substances participate in fission reactions. So knowing the difference between fission and fusion is important. Reading comprehension. Fission is you take big things and they break down into small things and it releases a lot of energy, right? So nuclear power plants, they do fission reactions with uranium and plutonium because those are really heavy elements. Fusion, on the other hand, are you going to take big things and turn into small things? No, it's the other way. You're taking small things and turning it into big things, and it releases a lot of energy. Fusion happens in our sun. Our sun, like the like solar system sun, right? Takes different isotopes of hydrogen, fuses them together to make helium, and it releases a butt ton of energy. While fission reactions, we are taking really heavy elements like uranium and plutonium. This is nuclear power, and those are fission reactions. So how you decide whether an element is going to participate in fusion or fission is by the mass defect of the nuclei. And so there's a graph in the textbook that it kind of looks like this. But what the big takeaway is at the apex of the graph, we have iron. Iron is the most stable nuclei. So that's why like stars that are dying or are running out of fuel, they have iron cores. Maybe it's why our globe, our Earth, has an iron core because iron is very, very stable. So basically any element lighter than iron typically undergoes fusion, while anything heavier than iron typically undergoes fission. All right, so that's just conceptually. With transmutation reactions, they balance the exact same as all the other reactions, nuclear reactions, where we make sure that the number of your mass numbers and your protons are conserved on your reactants and product side. Okay, all right, so that's the new stuff. Let me take a break for like a second and then think about what questions you want to do next. All right, so we're gonna, we got an hour left, so we'll skip around to midterms 1, 2, 3, or 4. So just think about what questions you want to do. I need to go to the bathroom, and then I'll be back in like 2 minutes. Okay, all right. So thanks for letting me take a break. All right, what midterm do you want to? 1, 1, 3, okay, all right. 4, okay, all of them, I guess? Okay. How many of you are going to move on to organic chemistry after? Yeah, most of you, okay. So I had a previous student of mine visit me. She just took her MCAT, and she told me, she said, Dr. N, I didn't think there'd be that much equilibrium on it. So I'm just pointing that out, all right? Okay. Okay. All right, so let's, yeah, okay, let's work through these quickly. All right, so midterm 1, this was solutions, energy of solutions, concentration calculations, colligative properties. So benzene was commonly used as an organic solvent. Which substances is predicted to be miscible with benzene? So the idea here is when your IMFs are strong between your solvent and solute, typically things, mix very well. So benzene, based upon the chemical formula, what are the dominating intermolecular forces present? There, LDF, and that's it. So do you think benzene will mix well with water? No. What about sodium nitrate? No. So our only answer here is going to be bromine, all right? Because bromine also has LDF. So the question is, why doesn't benzene mix with sodium nitrate? So sodium nitrate is what kind of substance? It's ionic. So salts typically will only dissolve in things like water because of what intermolecular force is created between water and a salt. Ion dipole. Oh, wait, what an ionic? Yes. So we are looking for ion dipole. So like water and sodium nitrate will mix, but not benzene and sodium nitrate because it is benzene is a non-polar substance. Okay. All right. Okay. Here's a concentration thing. All right. So let's just let's review like real quick. If I have something that's 5 molarity, what does that mean? 5 moles per 1 liter of solution. Okay. If I have something that's 5 little m, is that a typo? No. That means 5 moles over 1 kilogram of solvent. All right. If I have something that's 5 mass percent, what does that mean? 5 grams of solute over 100 grams of solution. Yes, very good. It's solution, not solvent. So therefore, you can actually figure out how much solvent do you have then. If 5 of your grams of your solution is solute, then that means 95 grams is your solvent, all right? Because they have to add up to 100, all right? What else? Mole fraction. What if I have a mole fraction that is 0.05? What does that mean? You have 0.05 moles of solute for every 1 mole of solution. That solution, again, is equal to 0.05 moles of solute. Therefore, 0.95 moles of solvent are present. All right, that's all of it together. All right, okay, so I'm gonna delete this. I'm deleting it. Okay, I'm deleting it. You can look at the video. Okay, all right. So I tell you, okay, we have this concentration of, what is that, potassium chromate. It has this density. What is the molality of the solution? So write the things you need. So if I tell you it's 0.872 molarity, that means I have 0.872 moles of what? K2CrO4, that's the solute, in 1 liter of solution, right? So when I give you a density, this density, 1.129 grams equals 1 milliliter of what? Solute? Solvent? No, of solution. That is what density means. It tells you the mass of the entire solution, not just the solute, not just the solvent, of the solution, all right? And that's important when molarity is involved because the denominator is solution. So what is our goal? We want molality, so let's just write what is our target. Molality of this solution, so little m, this is big M, has the unit moles of K2CrO4 over kilograms of solvent. Do we have one of those numbers already? Which one? Moles. So look, we're halfway done. We just need to figure out how many kilograms of solvent is there, right? And so that's where we're going to use these pieces of information. So we're going to have to use density. So if I have 1 liter of solution, that is also 100 milliliters of solution, right? So that density is going to help me go from the volume world to the mass world that we need. So I'm going to use that density. 1 milliliter of the solution weighs 1.129 grams. So that means this solution weighs, 1 liter of it is 1,129 grams of solution. Cool, so is that my denominator? Oh, I just have to convert it to kilograms, right? It's 1.129, is that right? No, what's wrong? This is grams of solution. We need grams of solvent. So what is the solution? The solution is the mass of your solute and your solvent. We just want the solvent component. That's all we want. So we need to figure out, oh, how much does the solute weigh? Just subtract that out, okay? Can we figure out how much the solute weighs? Probably, right? We're gonna actually use that mole amount, right? I know that there's 0.872 moles of solute present, K2CrO4. Do you know how much that weighs? We can figure it out, okay? So the mole amount's there. 1 mole of that junk is 194.19 grams. All right, so that equals something 196.3 grams of solute. Right, so we're going to use this number and this number, and we should be able to get that the solvent that is left over is something like 959.7 grams of water, right? So our solution is made up of 960 grams of water, 169 grams of the solute, and that gives us 1,100 grams of the solution. So this is the number that goes into the denominator, converted into kilograms. So molality equals the mole amount given, 0.872 moles over 0.9597 kilograms, and that is our molality, right? So this one's tricky because density is required, all right? I think there's a trick that I, a thing that I say where the units of like mole fraction, molality, percent mass, all of these things, they live on an island together where all you need is molar mass to figure out, to interconvert between these things. Molality, mole fraction, and mass percent. All you need is molar mass. But if you want to go to molarity, that guy lives on a different island and you have to use density in order to get there, right? So if you want to go from molarity to like molality or molarity to mass percent, you need density. But if you want to just convert between these guys, you don't need density, right? Okay, great. Okay. All right, so we'll just go in order. So 12. The heat required to separate solute particles is blah. The heat required to separate solvent particles is blah, and the enthalpy of mixing is that. Estimate the heat of solution for this process. So this is one of the equations we don't give you, so it's worth memorizing, that the delta H of your solution, this is what we observe in lab, like when we do coffee cup calorimetry. If our dissolution process is exothermic, when we do coffee cup calorimetry, which way does the temperature go? Up or down? Goes up, yes. Exothermic is a negative delta H. Our reaction releases energy, the cup gets hotter. But an endothermic dissolution reaction, the sign of delta H is positive, the temperature goes down because the reaction requires heat to get started. It's literally robbing the water of heat, that's why it gets colder. So the equation we use to look at the energetics of this reaction is delta H of solution, that is the exo versus endothermic thing in the cup, is delta H of your solute, so the energy to separate your solute particles, like the IMFs. Delta H of your solvent, so the intermolecular force of your solvent particles, plus delta H of mixing. So this is your IMFs of your solute and solvent together. So this term is an attractions term. So delta H of mixing is always a negative number because we're bringing attracted things close together. But solute and solvent, because we're breaking IMFs, these are always positive numbers. They're always endothermic. But it's the magnitude of these tell us whether a solution is overall exo or endothermic. So when your delta H of mixing is really strong, your delta H of solution is negative, it's an exothermic reaction. But when your delta H of mixing is weak, it's a small negative number, delta H of solution tends to be a positive number. So when we put all of this together, right, we can put those numbers in and just get, okay, solute is positive 138, plus your solvent is 220, and enthalpy of mixing is negative 398. So if we add these two numbers together, all right, 138 plus 220, all right? So here, your solute and your solvent, it requires 358 kilojoules of energy to separate your solute and your solvent. But when you mix them together, look how much energy you get back. You get nearly 400 kilojoules back. So what's stronger, the particles on their own or the particles together? Together. So because the particles in the solution together are stronger, this is going to be what kind of overall dissolution process? Exothermic. You can just tell from the math, all right? Versus if your solution makes weaker bonds, then this number is going to be a lot smaller. Your delta H of solution is going to be a positive number. And so we can look at like the magnitudes of the arrows. Like in the book, they talk about like, okay, here's your solute, here's your solvent. If your delta H of mixing is strong, it looks like this. So that means your delta H of solution is negative. But if you have a process where it's like, okay, solute, solvent, but like weak delta H of mixing, in this example, delta H of solution is a positive number, so it's endothermic, right? So that's what it is conceptually. Notice that solute and solvent, always positive numbers. It always requires energy to break IMFs, but it's the magnitudes of the mix versus the sum of the solute and solvent tell us whether a process is overall endo or exothermic. Okay, great. I want to go over, yeah, okay, we're just going to do this one. All right. All right, so we learned about solutions, making concentrations and solutions. So how do properties change as we make more concentrated solutions? So like, you know, we can have a like 1 molarity NaCl solution or a 5 molarity NaCl solution. So like, how do these two solutions differ from one another, right? We can talk about their vapor pressure. We can talk about boiling point temperature, freezing point temperature, or osmotic pressure. So how does the vapor pressure of water differ as we get more concentrated? Vapor pressure lowers, right? So if you're just remembering trends, it's called vapor pressure lowering, meaning as we get more concentrated, the vapor pressure of our solution, water, typically goes down. The reason is I don't want you to memorize this, it's actually the equation we use to calculate it, where the vapor pressure of your solution is equal to the mole fraction of your solvent that's present times the vapor pressure of that solvent, typically, right? So what we see here is as your concentration of your solute goes up, right? As you add more moles of junk to water, how does the mole fraction of water, your solvent, change? It goes down, because as you add more salt, less of your sample is now water. So that means as your concentration goes up, your mole fraction of water goes down, so therefore your vapor pressure goes down, right? Okay, so what do we call boiling point temp? What's the saying for that colligative property? It's boiling point elevation, yes, so it's elevation. And the reason is because of the equation, delta TB equals I times M, so the amount of particles in your solution, take into account strong electrolytes and the Van 't Hoff factor, KB, which is a constant. Then what do we call freezing point temp? Depression, yes, freezing point depression. So as things become more concentrated, freezing point temperature goes down. So delta TF, the negative, I don't want you to get tripped up on this negative sign. The negative sign is just there to remind you the temperature needs to go down, right? That's all it's there for. So it's just negative I times MKF. So if you do the calculation and you get a negative value, just remember, as your solution becomes more concentrated, the temperature goes down, right? So that means if you have a solution that has a high boiling point elevation, it will also have a very low freezing point depression, right? Those go along together, right? And then finally, osmotic pressure, it increases as concentration goes up, and the reason is the equation. Pi equals I times M RT, I think, right? So M is concentration, so as M increases, pi increases, osmotic pressure. Okay, so of these pair, choose the lower freezing point temperature. So negative I times M KF. We don't have to calculate a thing. So if I'm asking you the lower freezing point temperature, what kind of I times M are we looking for? Big, yes. Low freezing point temperature means lots of particles are dissolved because that's what's going to lower your freezing point. So we are looking for a large I times M product, right? So basically what we're asking is which sample has more dissolved particles, all right? If I said which one has the higher freezing point temperature, it's which one has less dissolved particles. So, okay, here are options, glycerin or pure water. Which one has more dissolved particles? Glycerin, obviously, because does pure water have any freezing point depression? No, it's gonna freeze at 0 degrees Celsius. Glycerin, though, on the other hand, regardless of the concentration, is going to freeze at a slightly lower temperature because its I times M is that. All right. Okay, next option, 0.2 glycerin or 0.2 KCl. It's the KCl. So the difference is here, notice both of them are the same M, same molality, but what's different about them? The I. So when you put glycerin into water, how many particles do you get out? 1. How do I know that? It's a non-electrolyte. But KCl is what kind of electrolyte? Strong. So you put 1 KCl in, you get 2 things out. So notice here, your I times M for KCl is larger because you get 2 particles. It's a BOGO deal. You put 1 in, you get 2 out. All right. All right, so now this time it's glycerin and KCl again, but the concentrations are different. So when we do I times M for the glycerin, because I is 1, Don't we get an I times M product of 0.2 for glycerin? Yeah. But then KCl, its I times M is equal to 2 times 0.1. Oh, yikes. So that is also 0.2. So how do we figure this out? Ion pairing. Yes, ion pairing gives us deviations. I know, this is so long ago. Hey, just take a moment and realize how far you guys come this semester. 1220 is such a hard class. Such a hard class. And you've learned so much this semester, right? Okay, I've been doing this for a very long time. So like I said, my hand knows what to do. Like my brain isn't even here. Okay, the lights are on, but no one's home right now. But yeah, do you remember deviations from the Van 't Hoff factor? I don't know, but you need to for the exam. So at first glance, you might look and be like, oh, they both have the same I times M. They both have the same freezing point depression, but they don't. One of them deviates from the Van 't Hoff factor, and which one is it? KCl. So what is its I times M? Is it greater than 0.2? Nope, it's less, because what is ion pairing? It is the idea that when you have a lot of particles in solution, remember you have cations and anions, they are attracted to one another. So when you have ions present, they might just pair up for like a brief second, slightly lowering the effective I Van 't Hoff factor. So for KCl, I actually isn't exactly equal to 2. It's actually slightly less than 2 because KCl can ion pair. Can glycerin ion pair? No, there are no ions. So its I times M is exactly 0.2. It has a Van 't Hoff factor of exactly 1. There's no deviations because of it can't ion pair, right? So yeah, so what's our answer here? Which one has the lower freezing point temperature? Which one has more particles? Glycerin, because it can't ion pair. So then it's the same treatment for this next one. You notice that both of them have I's of 2. Or do they? They don't. KCl can ion pair, so its I is slightly less than 2. Can calcium sulfate ion pair? Yes, it can, because it also contains ions. But is it this, so which one can ion pair more, I guess? It's the sulfate one, and the reason is because calcium sulfate is made up of higher charge stuff, so it ion pairs more. Those ions are more attracted to one another. So in this example, the KCl, ion pairs less. All right, yes, Van 't Hoff factor. So notice the only time we needed to use the Van 't Hoff factor, for these first two, did we have to use the Van 't Hoff factor? No, because their I times N were completely different, so it didn't matter. We only really use the Van 't Hoff factor when their I times M products are the same, and you just need to like differentiate one from the other. That's the only time you do it. Okay, all right, oh crap, we got 30 minutes. So can we go over mechanisms? Yeah, I won't do 15 mechanisms. Do we need to do this one? Initial rates, okay, fine. All right, so I'll do this one. This is the method of initial rates to get a rate law, right? But before I do that, let me just ask you, all right, if I have a rate law and A is second order, if I double the amount of A concentration, how does my rate change? Quadruples. What if my reaction is first order with respect to A? If I double my initial A concentration, what should happen? It doubles. What if I double the concentration of B? How does my rate change? It doesn't change because B isn't in it. So that's the treatment we're looking for number 16, all right? We want to see, all right, if I double O2, how does the rate change? So notice I deliberately picked a set of reactions where one of the other reactant stayed constant, because if NO stays constant, that's not affecting the rate law, or sorry, the initial rate. But what is the doubling of O2. So how does this rate change between experiments 2 and 3? Notice the exponents are changing, so don't just like be lazy about it. It's times 2, yeah. So that tells us that the order must be what? 1, because if I double O2 and I get a doubling of the rate, I can infer that the order is 1, but it's the order of what is 1? O2, because that's the thing that's changing. So are we done? No, we gotta get the other one, all right? So that's O2. So let's focus on NO. So notice that the first 2 reactions, O2 stays constant. So reactions 1 and 2, NO doubles. What happens to the rate? Does it double? No, it quadruples, right? You have your calculator. It quadruples. So that means NO is what order? Second. All right, so then rate equals K NO squared O2. Is that the full rate law? Almost. We just need K. How do we get K? Plug in any numbers from the table, at least just all one experiment. So what I could do is just take all of the numbers from experiment 3, plug them in, and get the value of K. So rate is 1.13 times 10 to the negative 1 equals K. That's what we're solving for. NO concentration 0.0252 squared, O2 0.0250. All right, and then just solve for K. And then that is your full rate law. It doesn't matter if you use reactions 1, 2, or 3. Okay. All right, so someone wanted mechanisms. All right, mechanisms is specifically for elementary reactions. So how we get a rate law has to come from experimental data. Is this experimental data? Yes, it is. So that's how we were able to get a rate law. What we can't do is just take a chemical reaction and be like, oh, that's our rate law. Because we don't actually know how these atoms are, or molecules are interacting with one another. It just so happens, yes, that this reaction's stoichiometry does match the rate law, but it doesn't always have to be that way. So what a mechanism is us just saying, hey, here are the simplest steps to this reaction. The rate determining step is the slowest step, and that's what dictates our chemical reaction. So if I give you this 2-step mechanism, all right, 2 steps are happening to one overall reaction. If we want the balanced chemical equation, we just add these 2 reactions up. So if we do that, NO3 cancels out. So the full balanced equation is simply 2 NOs plus an O2 gives us 2 NO2s. That's our balanced reaction. And then NO3, notice it's in the mechanism, but it's not in the balanced equation. NO3 is a what? Intermediate, yes, intermediate, because it's made and then consumed in the next step, all right? So then my question is, okay, there's basically 2 types of mechanism questions we can ask you. The first one is, okay, what if the first step is the slow step? What's the rate law? And then the second question is, what if the second step is the slow step? What is the rate law? So let's just explore both scenarios. So for the first one, if the slow step is the first step, the slow step is the rate determining step. As long as that step's an elementary reaction, that step dictates the rate law. So if the first step is the slow step, the rate of this reaction is K times NO times O2. So for mechanisms, elementary steps, this is the only time you are allowed to take stoichiometry and make them exponents. That's the only time, right, for elementary reactions. So if the second step is the slow step, that's the follow-up question. So this is the other type of mechanism we can ask you. So we're saying steps 2 is the slow step, all right? Then we do the same treatment, all right? Rate equals the concentration of the reactant. So K times NO3 times NO. Are we done? No, what's wrong? Can't have NO3. And so what we're gonna do is use the first step, which we're gonna assume is a fast equilibrium step, where we're gonna say that the forward rate is equal to the reverse rate. So we're gonna say K forward times NO times O2 equals the negative rate constant times NO3. And so writing this equilibrium step, the forward and the reverse reaction, it allows us to replace that intermediate that we can't have in that mechanism, all right? So we can see that, oh, we can replace NO3 with NO and O2. So rate equals, for this second step, slow step, you'll always have to do this fast equilibrium step if the second step is the slow step, is, I'm just gonna say K overall, they all combine, is NO2, oh wait, no, what am I doing? NO squared O2. Right? So that is the rate law if the second step is the slow step. So actually, let's put this all together. This is perfect, because I think, isn't this the same reaction as the previous question? It is, yes. So if 16, so which mechanism is consistent with this data? Yeah, so tell me, which mechanism, the first step is the slow step or the second step is the slow step, is consistent with the observations in question 16? Second step is the slow step, right? Because look, this second step, when we did this treatment, oh look, NO2 squared, O2. That's exactly what we got here in our observations, all right? So notice that this data does not match and is not consistent with the first step being the slow step, because if it was, it would be a 1-to-1 ratio. But no, it's the second step's the slow step. Cool? All right. All right, and then we did the catalyst stuff. Okay. All right, what's next? What topic's next? We got 25 minutes. What question or topic? Question 21? Okay. I want to do 19. Wait, what's 21? Yeah, okay, I want to do 19. All right. Okay. All right, so equilibrium. Yes. I just came from my Chem 1250 review session, which was also 2 hours. So that's why no one's home. And they learn chemical equilibrium. I'm so mad. We finish it in like a week and a half. We do like 3 lectures on chemical equilibrium. We cover ice tables. We cover weak acids and weak bases and pH and KSP. And that's just like, it's like 3 lecture days. That's it. How long have we been talking about big K? Forever. Yeah, so long. But remember what my previous student told me. She said, I didn't think the MCAT would have that much equilibrium on it. So, all right, so just putting that out there. So yeah, it pays off to be confident in ice tables. So here's a chemical equilibrium. We place 1 molarity of A in a rigid container. Where do you think that 1 molarity is going to go in our ice table? Which line? The I, yeah. Because when we tell you like equilibrium concentrations or pressures, we are very deliberate about it. You can't just assume that the concentrations I give you are equilibrium concentrations, unless I give you a pH. If I give you a pH, then that does represent equilibrium concentrations. But I just tell you, you place 1 molarity of A in a container. That 1 molarity is in the initial line. So if there's 1 molarity of A, there is 0 of B and C. 0 of B and C, okay? And I tell you, substance A decomposes at equilibrium. The concentration of B is this. So can I assume that this is an equilibrium concentration? Yes, because I specifically told you that B is this at equilibrium. So that is our hint to the ice table, and we're gonna like fill out the rest. So let's just kind of predict which way this reaction has to go. Has to go forward. So the change line is gonna look like what? 2x plus x plus x. So at equilibrium, 1 minus 2x, x. Right? And so like always, we want to write our K expression. So it's B concentration, C concentration, A concentration squared, but it's the equilibrium concentrations that go there. So Kc is equal to x squared over 1 minus 2x squared. Do I want to make an approximation here? No, why? We have x. Very good. I tried to trick you. I tried. Yeah, so in this example, we don't want to approximate. I know you guys got real good at it in chapter 16. Okay, you got real good at it. But here's the thing. I tell you what x is. I tell you B concentration at equilibrium is 0.025. I'm literally telling you what x is. So we can just plug in that number, all right? And then that's it. That's Kc. Right? So if you approximate here, you are just being lazy. All right? If you say, oh, the denominator is just 1. No, we know what x is. It should be 1 minus 2x. So I guess the answer is something like 0.025 squared over 1 minus 0.05 squared, and that equals something. I don't know. Whatever. 6.9 times 10 to the negative 4. All right? No need to approximate. Okay, the only time we might need to approximate or use the quadratic formula is when it's the other way. Notice this is like I give you information, tell me what K is. The only time we approximate, it's when it's the other way. I give you K and I ask like what is X or what is equilibrium concentration. That's like the only time you might need to approximate. Okay, I don't feel like doing that one. So let's do 21. Ugh. Okay. I actually put this on the midterm 2 Zoom review packet. I literally think I just copied it. Okay, so I tell you the Kc for this reaction is 10, meaning that at equilibrium, the products over reactants will have a ratio of 10. But I tell you, given the concentrations for the systems are blah, blah, and blah, one can conclude what? So, these are concentrations. Are they equilibrium concentrations? No, they're probably not, but let's check, all right? So how do we check? We calculate what? Q. Is Q special, different? It's the same thing as K, it's just not at equilibrium. So Q is also equal to ammonia concentration, nitrogen, hydrogen cubed. So all these numbers are 0.15 squared. No, that's not right. 0.25 squared, and then this is 0.15 to the 4th power. So, yeah, okay. So I get Q is 123. So is this reaction at equilibrium? Heck no, it's not at equilibrium. So if Q is 100 and K is 10, I have too much what right now? Product, so the reaction has to go backwards, perfect, all right? So what's the answer? It will go, I hate lefts and rights. The answer is B, goes to the left, right? So if the system was at equilibrium, then Q would be equal to K, if it was at equilibrium. But the reaction goes backwards in this example because Q is greater than K. So for A, if the reaction goes to the right, if it pushes itself forward, it's because Q is less than K. I don't have enough products, the reaction has to move forward, right? So remember all those, remember in this question I asked you, which way does this reaction have to go? And you all said what? Forward, because we have no products, right? And that tells you the signs of the change line. So if we go back to this question, and you told me, okay, this reaction has to go backwards. Let's write a change line. What would the change line look like? All right, if the reaction goes backwards, the change line looks like what? Minus under ammonia, 2x, and then under hydrogen, plus 3x, and nitrogen plus x. So once equilibrium is achieved, how do the equilibrium concentrations differ from initial conditions? How does the nitrogen concentration change? It's now higher than it was initially. What about hydrogen? Higher, because it went opposite, right? The change line, we lost ammonia, we gained reactants. And then the ammonia concentration is less, because it's minus 2x. And then the last thing here is, okay, once equilibrium is achieved, how is the hydrogen related to the nitrogen concentration? So let me just really quickly, I didn't actually put the initial line in. We don't actually have to calculate anything. So what were the initial concentrations? So this is ice. So 0.15, 0.15, and this was 0.25. So tell me, how does the equilibrium concentration of nitrogen differ from hydrogen? Which one's greater? It's going to be hydrogen, and the reason is because in the change line it is 3x. Because remember, the stoichiometry shows up in the change line in the conservation of mass in that ice table. Okay. Good, so that was 21. All right, someone wants a question for midterm 3. Okay, midterm 3. Do we need to do weak acids? No? 24. Okay. All right. Okay, so predict whether this salt will be acidic, basic, or neutral when dissolved in water. Okay, so for funsies. All right. If you put HF into water, the pH should be what? Acidic, very good. If you put H2NNH2 into water, the solution should be basic. How do you know? Because this thing is a weak base. How do I know it's a weak base? It's because I give you a Kb for it. It's a weak base. So you put HF in water, it has a Ka. It's a weak acid. It's going to be acidic. H2NNH2 has a Kb. It's a weak base. You put it in water, it's going to be basic. But what if I put F- into water? What is F-? It's a conjugate base of HF. So you put F- into water, what should the pH be? Basic. What if you put H2NNH3 plus into water? That's going to be acidic because that's the conjugate acid. All right? So this is the whole idea of like the conjugate of something weak is also weak. All right? The conjugate of a weak acid is a weak base. The conjugate of a weak base is a weak acid. So this is important because yes, I know HF is a weak acid. I know that other thing is a weak base. So when I look at this salt, all right, we need to think about what are the components of this salt. This salt is composed of H2NNH3 plus and F minus. All right, so both of these things are in solution. You just told me this thing is a what? Acid or base? It's an acid. And F minus is a base. Oh, so do they just cancel out and this thing's neutral? Not necessarily. We actually have to look at the Kas and Kbs, all right? We need to figure out which one's stronger. That would be easy enough, but I give you the Ka for HF. Did I put HF in water? No. So I actually need what? The Kb of F minus. And so how do I get the Kb? Use Kw. So Kw over Ka. Since I'm not really calculating anything, I can just use exponents. So if the Ka of HF is 10 to the negative 4, then Kb of F minus is going to be 10 to the negative 10. I don't actually need to calculate, I just need to get magnitudes. Because, okay, here's the Kb for this base, but I didn't put that into water. I put its conjugate acid into water. So I need the Ka of that junk. And so the Ka is equal to 10 to the negative what? 8-ish, yes. So tell me, which one is stronger? The acid or the base? What? The acid, yes, the acid is 10 to the negative 8. There's only 8 zeros and then a number, versus the base has 10 zeros and then a number. So the Ka is stronger here, all right? So basically, yeah, the acid component is stronger. So this thing is going to be acidic. Acidic. Cool? All right. And so the reason we have to do this is because both components are acidic and basic. Like, so if I said, okay, is NaF acidic or basic, what would you say? Basic. What makes it basic? F minus. What about Na? It's neutral, so we can ignore it, yes. But can we ignore no, you can't ignore them, so you actually have to look at both of them. Okay, all right. Cool. Let's talk about 25. Let's read this. Calculate the pH when we mix acetic acid and sodium hydroxide. Ka of acetic acid is that. Do we have to do a BCA table? Yes or no? Who thinks yes? Who thinks no? Okay, we have to do a BCA table. Dang it. How do we know when we have to use a BCA table? When there is something strong reacting, okay? If you have a strong acid or a strong base that you're mixing with something else, you have to do a BCA table because strong acids and strong bases react with stuff. BCA, it's before change after a reaction, all right? So that sodium hydroxide is gonna partially neutralize or fully neutralize that acetic acid. So we have to do a BCA table. So what are we mixing together? 50 times 0.2 is 10. Is it 10? 10 millimoles of acetic acid. And then we are mixing, what is that? 8 millimoles of strong base, so hydroxide. So we have a 10 millimoles of weak acid, 8 millimoles of strong base. What is left over after this reaction happens? 2 millimoles of HA and 8 millimoles of A minus. This, you have to do a BCA table. This is a lazy BCA table. I didn't actually write the whole thing out, all right, because the numbers are really easy, all right? So the question is, when you do the Henderson-Hasselbalch equation, what ratio do you do? Do you do 8 over 10? Nope, you do 8 over 2, because the Henderson-Hasselbalch equation, it's base over acid, but is it whatever base and whatever acid you want? No, it has to be the base and acid of the same system, right? It has to be acetic acid and its brother or cousin, sodium acetate, right? It can't just be acetic acid and sodium hydroxide. It has to be the same conjugate acid-base pair. So when you do the Henderson-Hasselbalch equation, the pH is equal to the pKa plus log base over acid, so 8 over 2. So it's not 8 over 10. That's the important thing, because a reaction is happening, all right? So for 26, do we have to do a BCA table? Yes? How do you know? HCl. So we're going to do the same treatment. How much pyridine is here? Is that 6? 6 millimoles of base. And then how much strong acid? This is 3? Is it 3? 3 millimoles of HCl. So HCl is a strong acid, so we have to BCA. So adding 3 millimoles of strong acid will turn, neutralize only half of that weak base that we have. So after this reaction, we should have 3 millimoles of base. And then what else? We converted some of that base into its conjugate, so 3 millimoles of HB plus. So when we do the Henderson-Hasselbalch pH equals pKa plus log base over acid, what's my ratio? It's 1, so 3 over 3. So it is not 6 over 3. If you do 6 over 3, you just chose whatever base and whatever acid you wanted, all right? You gotta actually do the neutralization if a strong acid or strong base is present. All right. Okay, so 27, do we have to do a BCA table? Yes, why? HCl, so just get the amounts, all right? So what is this? This is still 6 millimoles of base. And then how much acid is this? Can someone tell me? 6 times 0.1, is it 9? Okay. Okay, 9 millimoles of HCl. So, when these two things react, do we have any base left? No. So that means we converted all of the base into HB+, which is a weak acid. But what else do we have left over? The strong acid, how much? 3 millimoles. So if we have both of these things in our beaker, what is HB+? A weak acid. HCl is a strong acid. How do you calculate the pH of that? Strong acid, do we even care about this guy? No, so it's just the strong acid that dictates your pH. So if you think about like where this is on the titration curve, actually it's over here, okay, if it's this. Where is this on the titration curve? Is it before your equivalence point? It's after your equivalence point. This is where the strong titrant dictates your pH. So do I just negative log this number? No, you actually have to get the concentration. So the HCl concentration after this neutralization reaction is 3 millimoles over what, 100 milliliters? So this is the number that you negative log, and then you get a pH, and it should be acidic. Okay, all right. All right, then 28. Do I have to do a BCA table here? Yes, why? There's strong junk there, yes. But this one's different because look, is there anything weak here? No, there's not. But we still actually have to do a BCA table because there's a strong acid and a strong base. Do those react with one another? Heck yes, they do. And so we need to calculate which thing is left over. That's going to dictate our pH. So how much HCl is here? Is that 10? 10 millimoles of HCl. And then what is this? No, it's not 10, is it? What is it? 8? What? I don't know where my notes are. My stapler ran out. Now my life is over. It's what? 10 and 3, thank you. 10 millimoles of HCl, 3 millimoles of what? Of what? Of CaOH2. So I'm gonna make it easier on myself, right? Because I know like H plus reacts with OH minus, but this is calcium hydroxide. So how much hydroxide is actually here? 6 millimoles of hydroxide. So tell me, when these two things react, what's left over? HCl, 4 millimoles of HCl. And that is what's going to dictate our pH, because when we mix a strong acid and a strong base, the salt that's created is just a pH neutral salt, so we can just ignore it. So we just want to calculate what is the H plus concentration after this reaction. So we're going to take whatever's excess, in this case it's HCl, and calculate the concentration. So what is this? Over 65 milliliters. And then whatever that concentration is will give us our pH. All right. So this one, we don't even need the Henderson-Hasselbalch equation. All right. The giveaway that we don't use the Henderson-Hasselbalch equation is, do I give you a Ka? No. All right. Strong acids and strong bases don't have Kas. so that you can't use the Henderson-Hasselbalch equation. You just have to do a BCA table. Okay, so I guess we're done. Yeah, we're done? All right. Okay, good luck, everybody. Yeah. What's up?
Sorry.